Assalamualaikum warahmatullahi wabarakatuh. A very good day I bid to my dear students. Welcome to Lepton Meka SES Semester 2 Session 2020-2021. Today we are going to do a few example questions from Chapter 5, Magnetism and Electromagnetic Induction. Let's jump straight into it. So question 1. We have two very long straight wires carry current as shown in the figure below. Okay, so in this figure, what do we have? So we have I1 here. So this is our I1 with a magnitude of 10 ampere, and we have I2. Okay, both wire, the direction of current is upward. Okay, then we have point X, and we have 8 centimeter. This is the distance between wire that carrying current I1 and also wire carrying current I2, and 15 centimeter is the distance from wire carrying current I1 to point X. Okay, and then number 1, calculate the magnitude and direction of the magnetic field at point X due to wire carrying current I1. And number 2, if the magnitude of magnetic field produced due to wire carrying current I2 at point X is 4 times 10 power of negative 5 Tesla, determine the value of I2. Okay, so we have two sub-questions. Let's do it one by one. So for the first sub-question, calculate the magnitude and direction of the magnetic field. Okay, so here the question asks us to find the magnetic field, which is B, due to wire carries current I1. So this is B1. Okay, so the formula to find the magnetic field for a straight wire is B1 equal to mu naught I1 divided by 2 pi R1, where I1 is the current, the magnitude of current in the wire, where R1 here is the perpendicular distance between wire I1 and also point X, which is this value here. So this is our R1, the perpendicular distance between the wire and the point. Okay, and then so this is I1. So we have all the necessary information that we need. So we only need to substitute everything. So mu naught is 4 pi times 10 to the power of negative 7 multiplied by the magnitude of I1, which is 10 ampere. Okay, divided by 2 pi multiplied by R1. Remember, okay, the given information here, the R1 given is in centimeter. We must convert it into meter. And then we get the final answer, which is 1.33 times 10 to the power of negative 5 Tesla. Don't forget the unit, because if you lose the unit, then you are losing the marks, right? So that is only the magnitude. How about the direction? Okay, so for a straight wire like this, to determine the direction at point X, we need to use our right hand grip rule. Okay, right hand grip rule, where if you grip your right hand, okay, your thumb is pointing to the direction of current, which is upward. So this is the direction of current. So you should have, okay, let me use another color for this one. You should have a magnetic field in counterclockwise direction, like this. Okay, so at point X it should be like this. So this is just an imagination. So this is into the page, right? So the direction of the magnetic field at point X due to current I1 is into the page, right? And then part 2, if the magnitude of magnetic field produced due to wire carrying current I2 at point X is 4 times 10 to the power of negative 5 Tesla, determine the value of I2. Okay, this time we are given the value of magnetic field. So this value here is actually B2, which is produced by current I2. Okay, we already have the direction upward, but how about the magnitude? So here we can use the same formula again. B2 is equal to mu naught I2 over 2 pi R2. But what is R2? R2, remember, it is the perpendicular distance between the wire and the point. So this is actually R2, which is 15 minus 8, we get 7 centimeter. Okay, and then when we substitute our values, remember again, don't forget to change your centimeter to meter, and then you can find the magnitude of I2, which is 14 ampere. Now, on to question 2. So we have a 30 centimeter rod PQ moving at velocity 45 meter per second across a uniform magnetic field 0.8 Tesla. Okay, so let me try to represent this situation that we have. So let's say this is our rod PQ. So the rod has length of 30 centimeter. Okay, and then let's say it is moving to the right. Okay, this is just a representation. So V is 45 meter per second across a uniform magnetic field. I want to draw the magnetic field, let's say into the base. So this is the uniform magnetic field. Okay, I'm sorry, is this drawing is a bit bad, but that's fine, just to get a rough idea of what's happening. Okay, so this is what happening. The rod is moving across uniform magnetic field of 0.8 Tesla. So B 0.8 Tesla. Okay. So this 30 centimeter rod. So this 30 centimeter represent our length. Okay, our length. And then the velocity 45 centimeter. This is our V. Sorry, 45 meter per second. My bad. And the uniform magnetic field is our B. Okay. And then number 1, calculate the induced EMF. So for a straight conductor like this, the formula is induced EMF is equal to BLB sine theta, where theta is the angle between the magnetic field and the velocity. Here, from our representation, from our diagram, from what I sketched, the theta is 90 degrees. They are perpendicular to each other. Okay, so substitute the values. Magnetic field, we have 0.8 Tesla with the length of 30 centimeter. You convert it into meter here, so you get 0.3 meter, and then velocity is 45 meter per second with an angle 90 degrees. So substitute the values here. Don't forget, okay, sometimes when you do other question, your mode is in radian, but here make sure you convert it into degrees again, and then you should get 10.8 volts. So that is the induced EMF. And number 2, determine the induced current if the resistance in the rod is 15 ohm. Right. So here we use our Ohm's law. So induced EMF is equal to induced current multiplied by the resistor. Okay, we need to find the induced current. So you can substitute the values and we can find the final answer, which is 0.72 ampere. And question 3. So we have a narrow coil of 50 turns and diameter of 8 cm is placed perpendicular to a uniform magnetic field of 2 Tesla. After 2 seconds, the diameter of the coil is decreased to 5 cm. Calculate the induced EMF. Okay, so what do we have here? So the 50 turn, this is our N, capital N, the number of turns, and okay, diameter of 8 centimeter. Okay, so from this case, the diameter of the coil is changing. So that means the area is changing. Therefore, the magnetic flux is changing. When we have a change in magnetic flux, we will have induced EMF. So here, the diameter of 8 centimeter is actually the initial diameter. Okay, and then place perpendicular. So it shows that the theta is 90 degrees to the magnetic field. Okay, and then the magnetic field has a magnitude of 2 Tesla. This is B. Okay, 0.2 second is our time, and then 5 centimeter here is the final diameter. Okay, calculate the induced EMF again. We need to find first the initial area. Okay, so initial area AI is equal to pi d squared over 4. Here our d is our initial diameter, di, so di squared. Then we get 5.03 times 10 to the power of negative 3 meters squared. So this is the initial area. Next, we can find the final area, which is again the same formula, pi d squared over 4, but this time this is df, final diameter. So we should get 1.96 times 10 to the power of negative 3 meter. And then we can find the change in area, which is final minus initial, always finals minus initial. So 1.96 minus 5.03 times 10 to the power of negative 3 over 0.2 second. So we should get negative value because the diameter is decreasing. The final is smaller than the initial. So we get a negative value here. Okay, and then substitute into the formula, which is induced EMF is equal to negative NB cos theta dA over dt, because this time what's changing is our area. Okay, and so we substitute the values. Our theta here is 0 degrees because theta is the angle between B and A. B is perpendicular to the magnetic field. The vector B and A is 0 degrees because the angle between the normal to the coil and the magnetic field is parallel. Okay, theta is the angle between normal to the plane and the magnetic field. So we get 0 degrees here, and we get the induced EMF to be 1.5 volt, which only makes sense that we have a positive value here, because when the diameter is decreasing, our magnetic flux is decreasing. Okay, so induced EMF will try to add again what is being decreasing so that it doesn't change. Okay, so that's the final answer, right? I think that is all for this session. I wish you all good luck for the upcoming PSPM2. Thank you, and Assalamualaikum warahmatullahi wabarakatuh.